Hello, my name is Isabel Chapa. I am an incoming junior at the University of Texas at Austin studying chemical engineering. My research project during this REU was over dopant-dopant exchange coupling in manganese-doped cesium-lead chloride perovskites as part of the Lee group. For context, my project is based on a paper published by the Gamlin group, who is another research group here at UW. This paper observed manganese dopants as chlorine was exchanged for bromine. During this exchange, there was a clustering of cesium-manganese chloride. This paper came to the conclusion that this occurs due to a stronger bond strength between manganese and chlorine in comparison to manganese and bromine. My project is understanding the atomic interactions of these structures. Other literature suggests that coupling occurs between manganese ions. This happens when two magnetic atoms interact with each other. Atoms become magnetic when unpaired electrons move about the nucleus, producing a magnetic field. Perovskites are new materials with lots of applications. Some include photovoltaics, LEDs, solar to fuel energy conversion, as a catalyst, batteries, superconductors, radiation detectors, and data storage. In short, perovskites have several applications that are more efficient and cheaper than materials currently being used. Research is being done so we can control these materials. The use of dopants like manganese is one way to manipulate these materials to do what we want them to do. So investigation on their effects provides an understanding of the material. My research this summer was computational. The simulation software I used is Vienna Ab Initio Simulation Package, otherwise known as VASP. VASP uses something called density functional theory, or DFT, which is a computational quantum mechanical modeling method. A key component of DFT is electron density. I included this water molecule as an explanation of DFT. In chemistry class, we learned that oxygen is an electronegative element and therefore attracts more electrons to its nucleus. So in water, we interpret oxygen to be partially negative due to the electrons being more concentrated in comparison to hydrogen. The electron density of this water molecule tells us how it will interact in other systems due to the partial charges in the structure. So, much like the electron density gives us an understanding of this one molecule, it can give us an understanding of more complex systems like my project. For my project, I was given an optimized structure of cesium-lead chloride with just one manganese dopant. I inserted the second manganese dopant in 3 positions. In this particular structure, manganese will replace lead because their charges are the same, which would lead to a stable similar structure. The first position is the shortest distance, which is across one axis. The second is 2 axes, and the third 3. Based on these 3 distances, some of the other atoms may interfere with the strength of coupling. In addition, larger distances greater than 5 angstroms will have less coupling strength since the dopants will not be as close to each other. This is a closer look into the medium distance, which is the second dopant across 2 axes. The first step in computational work is optimizing the structure. Computational work involves intuition. Although the computer is solving a lot of math equations, it will make physically impossible structures without proper input. So every calculation you submit, it's important to have an idea of what you should expect. For this particular system, I am expecting symmetry in bond lengths between manganese dopants and the surrounding chloride atoms. This data I am showing is for the medium distance again. There are 2 structures, one with antiferromatic coupling and one with ferromatic. The difference is that antiferromatic is opposite spins, meaning magnetic moment is up in one manganese and down for the other, and ferromatic is same spin, so both dopants have magnetic moment in the same direction. Across both of these structures, symmetry was conserved during geometry optimization. This means I could continue on to other calculations with these structures. One of the calculations I am doing at the moment is density of states plots. Density of states is the number of different states at a particular energy level that electrons are allowed to occupy. For this particular structure, we know that manganese dopants have an unpaired electron in the d orbital, since that is where the magnetic moment is coming from. So we would expect the plot to show a d orbital of manganese to have a higher number of different states due to the d orbital not being completely full. This summer has been a great experience for me, and I would like to thank a few individuals, my PI, Dr. Shenzhen Lee, my mentors, Dr. Chad Hoyer and Dr. Ryan Beck. Thank you to Danica Hendrickson, and thank you to MEM-C for giving the opportunity to do research this summer.